Welcome to CSC 201, Lesson 4.4, Direct Proof and Counterexample Part 4, Divisibility. Let's start with the definition of divisibility. If n and d are integers, then n is divisible by d if and only if n equals d times some integer, and d is not 0. So this was the definition of even when d was 2, right? So we said if n was an integer and you were dividing by 2, right, n is divisible by 2 if and only if n equals 2 times some integer. So now we're saying, we're generalizing this definition to n is divisible by some divisor d if and only if n equals d times some integer with d non-zero. And there are many ways that we say this and that you have learned to say this throughout your math education. N is divisible by d also means that n is a multiple of d is a factor of n, d is a divisor of n, or d divides n. So this last one, d divides n, we have a new notation for. The notation d vertical line n is read d divides n. And then symbolically, we would say for all n and d in z, so for all integers n and d divides n if and only if there exists some k in z such that n equals d times k and d is non-zero. So n is a multiple of d, an integer multiple of d non-zero. And then if we write d and then the vertical line with a slash, we read d does not divide n. Okay, so some basic questions about divisibility. Is 21 divisible by 3? Yes, because 21 is 3 times 7. Right, it's an integer multiple of 3. And does 5 divide 40? Yes, because 40 is 5 times 8. And does 7 divide 42? Yes, because 42 can be written as a multiple of 7. 7 times 6. Is 32 a multiple of negative 16? Yes, because 32 is negative 16 times 2. So this definition of multiple or divides can apply to negative numbers as well, right? The definition says n and d in the integers. And integers include negatives. Is 6 a factor of 54? Yes, because 54 equals 6 times 9. Is 7 a factor of negative 7? Yes, because negative 7 equals 7 times negative 1. For any non-zero integer k, does k divide 0? So that's saying, does k go into 0, or is k a factor of 0? That's yes. Okay, yes, because 0 equals k times 0. Now, does 0 divide any number? That's a no, right? 0 cannot divide any number. You can't divide by 0. Does 4 divide 15? That's a no, okay? Because you cannot write 15 as 4 times an integer. All right, so prove or disprove. For any integers a and b, 3a plus 3b is divisible by 3. So this is going to be very similar to our even and odd proofs. Like if we were trying to prove 3a plus 3b is even or odd, we're trying to make it look like 2k or 2k plus 1. If you're trying to prove that it's divisible by 3, you need to make it look like it's 3 times an integer, 3k. Okay, so let's suppose a and b are elements of the integers. Then 3a plus 3b could be rewritten as 3 times a plus b. And since a plus b is an integer, I have written 3a plus 3b as 3 times an integer, which means 3a plus 3b is divisible by 3. Prove for all integers a, b, and c, if a divides b and b divides c, then a divides c. So let's suppose the if part. So suppose a, b, and c are integers, and a divides b and b divides c. We need to show that a also divides c. So let's see. If a divides b, then b is a times some integer. B is a multiple of a. And if b divides c, then c is a multiple of some integer. Thus, c, which is b times j, now I'm just going to make a substitution. Instead of a b right here, I'm going to replace the b with a times k. I'm just going to do a substitution. So this is going to be, instead of b, I have ak times j, which is a times kj. Now, since kj is an integer, I have written c as a times an integer, which tells me that c is a multiple of a, or a divides c. C is a multiple of a, and thus a divides c. Prove for all integers a and b. Prove or disprove for all integers a and b. If a divides b and b divides a, then a equals b. So prove or disprove, so we'll start with some tests. A divides b and b divides a. So a is a multiple of b and b is a multiple of a. So it seems like they'd be equal, like if they were both 4, right? If a equals 4 and b equals 4, then a divides b because b is a multiple of a. Right, because 4 equals 4 times 1, and b divides a because, again, 4 equals 4 times 1. So this has me thinking that this might be true, that a equals b. But this has to be true for all integers a and b. So what if I throw some negatives in here? What if a is 4 and b is negative 4? So does a divide b? Yes, because a goes into b. So that means b, which is negative 4, can be rewritten as a 4 times negative 1. Right, so this is b equals 4 times an integer. And then does b divide a? So that would tell me that b goes into a, right? So a can be rewritten as b times an integer. A is 4, b is negative 4 times negative 1. And yeah, a does divide b and b does divide a, but a and b are not equal. 4 does not equal negative 4. So this is our counter example. Okay, the fundamental theorem of arithmetic says that any integer greater than 1 either is prime or can be written as a unique product of primes. So that composite numbers can be written as a unique product of primes. For example, 72 can be written as a product of primes as 2 times 2 times 2 times 3 times 3. And there is no other prime factorization of 72. There's no other way to do it. And it's called the fundamental theorem of arithmetic. And this, the fundamental theorem of arithmetic, is why we say that 1 cannot be prime. Okay, because if 1 were prime, the fundamental theorem of arithmetic would not hold. It would not be a unique factorization, because I could go, there's another factorization, and there's another, and there's another, right? Because you could just keep doing 1 times 1, and you would have another different factorization of a composite number. So if we keep 1 out of the list of primes, then every composite number has a unique prime factorization. And then the standard form of an integer n, when we write it in its prime factorization, the standard form is to write the factors in ascending order from left to right. So I did the 2's first, right? That's the smallest prime, and then I did the 3's. So ascending order, smallest prime to biggest prime. So 2 cubed times 3 squared. Either of these is considered standard form for a prime factorization. Prove or disprove. If a 2-digit number is divisible by 9, then the sum of its digits must be divisible by 9. Now, this might be a little divisibility trick that you're already familiar with. A lot of people learn this somewhere along the way, sometimes in elementary school, that numbers that are divisible by 9 have the sum of their digits divisible by 9. So we'll do a couple little tests just to convince ourselves. Like a number that's divisible by 9 might be 63. The sum of its digits would be 6 plus 3. Divisible by 9, divisible by 9. Another number that's divisible by 9, 81. The sum of its digits, divisible by 9. 900, that's divisible by 9. It's 9 times 100. And 9 plus 0 plus 0, divisible by 9. All right, so I'm convinced, based on my past knowledge and a few tests. So some scratch work. If x is a 2-digit number, a 2-digit number looks like A, B, right? This is the tens digit, and this is the ones digit. But with our mathematical notation right now, it kind of looks like A times B, which that's not the case, right? It really is, A is in the tens digit, so it's really 10A, right? Because if it's 63, 6, 3, that 6 really represents a 60, so it's 10 times 6, and then plus the ones. So 10A plus B. And we know, we're going to suppose that 9 divides 10A plus B. And we're going to argue, and we need to show that 9 divides A plus B. Okay, so if 9 divides 10A plus B, so looking at this right here, that means that 10A plus B is a multiple of 9. And again, what I need to show is that A plus B is a multiple of 9. It is 9 times some integer. Okay, so we've done a problem similar to this before where we have an equation that relates A and B. 10A plus B is 9K. I really only want A plus B to be 9 times an integer. Like I want the left side of this equation to just be a plus b. I have 10a plus b. I've got too many a's. So what can I do? Subtract off the a's that I want to get rid of, as long as I do it to both sides. So I only want one a, so I'm going to subtract 9 a's so that I have a plus b, and that's going to be 9k minus 9a. And that is 9 times an integer. K minus a is an integer, so a plus b is a multiple of 9. Okay, so that's my scratch work. I want to write it up nicely, stating all the details and writing sentences so that a reader can understand this proof. So we're going to suppose x is a 2-digit number with tens digit a and ones digit b. Further, suppose x is divisible by 9. Then x equals 10a plus b, and 10a plus b is a multiple of 9. Subtracting 9a from both sides yields a plus b equal 9k minus 9a equals 9 times k minus a. And since k minus a is an integer, a plus b is divisible by 9.